Ladies and gentlemen, and welcome to Taiwan Taipei Tech. My presentation is about the X-Wings. Actually, is about the drones. It's Xilinx FPGA based AIoT drones. And I like the X-Wings, the name very much. It's like a Star Wars drones, right? Which is very good name for the satellite communication control drone. So let me introduce myself first. I created a lab called the AIoT lab. My research was originally about the computer vision, and I have visited Columbia University before. And after I joined Taipei Tech, I think the future is about drone. I joined Taipei Tech around 6 years ago. So I start to research drone and combine AI and the IoT communication with the drones. Okay, so I also have a drone operator license. So here is my publications. My systems, my platform is called AI Wings, which we integrate with the drones and the 5G communications. So here's the drone system. I have a demo video. So this was for AIoT application. We have a cloud interface which can control the drone and use the OpenStreetMap. Camera is a little bit old, so we don't have a stabilizer. A keyboard, we don't have keyboard at that time. But right now I have figured out where DIY keyboard. Okay, so let's fast forward this video. Our goal is to drop the AD case. There's an emergency. Okay, so that's the idea, that's the demonstration of our system. So I published a paper on the IEEE Systems Journal in 2022. So here is our system. Actually, it's a DIY system. We mainly based on the Audio Pilot. Audio Pilot is a very reliable open source unmanned vehicle system. If you watch some videos from Ukraine, you can see the control system of the mission planner and the audio pilot. They use a lot of audio pilot. It's a very great open source system. So our idea is to integrate an audio pilot system with an embedded system. It's called a companion computer. We use the Android system, Android mobile phone as a companion computer because it has embedded 5G communication, and also it has support AI acceleration. Right? So it's basically a very powerful and a lightweight computer, companion computer. So we developed the Android software which can communicate with the drone cloud, and also we support TensorFlow mobile for AI models, and we implement the 4G, 5G remote commanding of the drones. So we use a Mavlink communication protocol to control our drone. We have built the drones with different size, but if we want to communicate with our satellite, maybe we need a bigger drone or smaller receivers. Right now, it can only carry around like 3 to 5 kg of our drones. And based on our platform, we have developed many applications. One of the applications is a Guardian drone. It's for police which we can control the siren and the speaker to send messages through the drones. Okay. And also we will try to simulate the drones in a virtual world. So we try to build the digital twins with our drones. We can watch another video here. 1 second while the video is removed. Anyway, so from this picture, you can see that the upper left corner, the image of the upper left corner is the real drones here. And then this is the digital twin of our campus. So we sync the video with the digital twin world. But the 3D models was captured from Google Earth. At that time, the Google Earth does not have a detailed, they have much better detailed map of the world right now, of Taipei right now. At that time, the trees are connected together, but you can see the size or the appearance of the buildings. So this is from Google Earth, and this is the OpenStreetMap. Here's the control, the video on the control UI of our system. You can see different videos. So why we are building the digital twins? Because we want to train the AI to identify objects like tanks, right? Although today we have a lot of data set and we have a lot of videos from Ukraine, but the data set is not enough, especially the bird's eye view. So we use the game engine, right? Unreal Engine. The system is a very powerful and popular game engine, and Microsoft has developed a plugin which allows to do drone simulation. It's called AirSim. So we use AirSim and we put a lot of military objects into the world. So here is a simulation result, and then we use the Google Earth. Okay. So Google is busy on capturing the world. So right now they have a 3D version for Google Map, right? So here, so we can use the data for simulation. Okay. And I have proposed a method because today we have 3D words and generated images. So I propose an algorithm called generative XR transfer learning, which will try to select the best samples among the 3D models and the generated images, and then use the images to train object detection. Although today's AI has become more and powerful and become multi-model, but for object detection, original architecture like YOLO still works better than the transformer architecture. And then the generative images sometimes generate very unrealistic images. Although the images we human can identify the difference between real and generated images most of the time, but it's also still helpful for AI to identify objects. Because the first step of a convolutional neural network is to remove the details, right? They try to capture the features. So although the generative image looks different, like the shadows, the lighting are different from real images, but the features are the same. So the generative, if we use generative models, generative LLM to train object detectors is still helpful. Okay. And we have used the generative XR learning to train the tank object detector and apply it to real videos. Those are the training results. Originally, they are the training data length of the bird's eye view videos. After we enhanced with simulations, with VR images and XR images, then we can successfully identify the tank or track the tanks. We mix the VR data with the real world data, so there are different ratios. Basically, it can improve a lot, improve the detection result a lot. Okay, so let's continue. We also built some search and rescue scene. We have built many simulation environment which can train AI. But for we try to use reinforcement learning, but 3D world is not good for reinforcement learning. First, it's too slow, and it's hard to reproduce all the details. Like the drone may go through the trees. Right? Although we try to model all the tree models, but it will go through the leaves or go through the fires. But still, it's good for the vision object detection. So it's good for the visual recognition, like segmentation, object detection. Okay, so our next step is to combine the drone, the AI wings, with B5G LEO communications. We have co-work with TASA, try and communicate with the satellite in our satellite communication device in our department to build the satellite controllable drones. Here's the TASA truck, but it's still under construction. So for demo reason, we just shows the internet control of drones. But if we have the device are ready, because I'm control over the top of the internet, right? So it will be no problem to migrate from the internet to the LEO network. So after the AI wings, our next generation of drones is based on FPGA. FPGA has many variants. First is flexible. We can design any hardware device architecture on FPGA, and also it's a very low power. Low power is very important for drones, because it can allow the drone to fly longer, right? The battery power is very important for the drones. So here is the video. So we create a FPGA drone here. We use a big FPGA because we are part of a short-out project. I try to purchase new FPGA this semester. First, we develop a multi-video stream. There are 2 videos. The third is local camera. I have 2 cameras on top of the. I use the USB camera right now, and I use Wi-Fi to receive the signal. The 5G is not ready yet. Also, we have built in the tracking algorithm. Give source. I have a project that I try to capture smaller. Try to use the camera to computer vision to identify the drone. But I find it's not a good idea. Most of the drones are too small. If the drone is flying high in the sky, it's easy to identify. If the background is complicated, it's not very easy to identify the drone. Anyway, we can run a field object detection on FPGA. Okay, so let's our FPGA drone. Let me briefly introduce the architecture. So the key is the Xilinx FPGA or FPGA. Xilinx FPGA is now called MP SoC. It's as a built-in SoC operating system. It's as a Linux system, and the system can be it's very useful because most control can be running on the Linux, and we use the operating system to communicate with the Mavlink, the audio pilot. The audio pilot system is now called Pixhawk. So we use Mavlink protocol to communicate with the Pixhawk flight controller. Right? And there's a deep learning acceleration unit called the DPU. DPU is we use the DPU to run the YOLO object detection and deep sort tracking algorithms. So we also support 2 cameras, multi-camera streaming. But right now the streaming need to go through the embedded Linux, and we need a hardware video encoder like H.265 in the future. We use a Wi-Fi connection and the USB camera streaming. Okay, so it's a hardware architecture. For Xilinx, they have a Zinc processor. The main part is a Zinc processor, which run many software and embedded Linux inside. And the other one is the DPU process. Other things are interconnection or the ARM bars between those 2 architecture. So right now we haven't developed enough hardware for videos or the peripherals, but mostly we are using the Linux, the Zinc processor for most processing, and then the DPU. About the deep sort tracking, although Xilinx has improved faster than before, but the AI algorithms has improved very fast. So there's many modern architecture or unit like the sigmoid weighted linear unit activation cannot be directly applied on Xilinx on the DPU. We need to use the DPU to run our AI algorithms, AI models. But so far it has support until YOLO V7 or V4 or V5. And for V7, the activation function is not support. We can change the activation function, but the accuracy will drop, right? So still we are running mostly on YOLO V4. And also we use the deep sort. Deep sort is based on the command filter to predict the next position of the target, and then we will update the features. Deep sort is combine the deep learning features with the command filter prediction. For drones are very difficult to predict, especially the multi-rotor, because it can change the direction a lot. Very agile, hard to predict. Okay, so here is the conclusions of my current work. So first, the FPGA is power efficient and flexible, right? And can integrate many parts. Theoretically, I can integrate the controller, the communication part, and the AI together in one FPGA chip. So our goal is to integrate with the orbit satellite in the future. However, it's a very challenging, because for each part or communicate with peripheral, we need to have an IP. And right now, I think it's length of the video encoders. Right now, I'm just pasting the motion JPEG through Wi-Fi, and it's not very efficient for an IoT architecture. And also, in the future, we want to integrate with the Pixhawk. Pixhawk is based on a microcontroller, STM32. And we can integrate the STM32 with other functions inside one chip. And then our drone will be very power efficient, right, and low cost. But there are a lot of sensors on the Pixhawk. So it's not easy to integrate with the whole systems. But anyway, it's important. I think it's has a potential, very great potential for FPGA drones in the future. Okay. So if you are interested, or other students are interested in our project, you are welcome to join our project. Okay, so thank you. This is my presentation about our research on FPGA drone.